Hi everybody, in this video I will talk about what a real gas is. If you remember in the previous video, in the ideal gas law, attractive forces between molecules are essentially ignored, and in addition, the molecular sizes in an ideal gas is considered to be very close to zero, so we ignore both the attractive forces and the molecular sizes in the ideal gas law. Now, what happens if a gas experiences attractive forces and has a significant molecular size compared to the volume of the container? If this happens, then the gas kind of goes off the rails and doesn't behave as an ideal gas anymore. Instead, it behaves as a real gas. A real gas is a gas that does not follow the ideal gas law because the attractive forces and the molecular sizes of the gas particles alter and skew the ideal volume and pressure. So in the first image here, you see PV equals nRT. That is, of course, the ideal gas law. But what happens if the P and V are skewed or made, different because of attractive forces and molecular sizes? Well, what ends up happening is that you have a second equation that is used to correct the pressure measured and the volume measured in order to make them ideal again. So you might be asking, how exactly do attractive forces and molecular size skew our pressure and volume? Well, let me tell you. So in this box of text right here, you can read it, and I'll read it for you. It says, the pressure measured, so the pressure that we measure on the container, is slightly lowered by the attractive forces which pull the gas particles closer to each other and away from the container, and this decreases their impact on the container. And if the impact on the container decreases, the force on the container decreases, so it decreases the overall pressure. So, therefore, in order to correct the pressure that we measure, since this pressure was lowered by the attractive forces, we can add an an squared over b squared term to the pressure measured in order to counteract the decrease in pressure caused by attractive forces and correct it back to its ideal conditions. So in a way, you can think of this pressure as wanting to be as ideal as possible, but some evil thing called attractive forces caused the pressure to decrease. So it wants to become ideal again. So in order to counteract the decrease, it adds this an squared over b squared term in order to make it ideal again. So think of this as the same thing as this. So the measured pressure plus this term will give us back the ideal pressure, or the pressure that we want in the first place. Now, what about volume? Well, the volume that we measure is going to be this term over here. It's going to be volume of the container measured. But let's read this text to see what happened exactly to the volume to make it not ideal. The volume of the container is usually the volume that particles have to move around, because if you think about it, the container, assuming that the particles are super duper small, is basically the volume that the particles can travel in. But when the gas particles get significantly large relative to the volume of the container, so they're super huge, then the volume of the container, which is this over here, is greater than the actual space the particles can move around in. So notice how the volume of the container, which is this box, is greater than the space that the molecules can move in, because as you can see, the molecules actually take up space now, and molecules can't move through themselves, so they take up space, and thus the space they have to move around is much lower because they can't move through each other. They can only move, around each other, and that's less than the volume of the container. Therefore, the measured volume of the container is subtracted by NB in order to get the volume the particles can move around in, which is the ideal volume experienced by the gases. So by subtracting the volume measured, which is the volume of the container, minus the volume of the particles, which is NB, then you essentially get the ideal volume experienced by the gas. So this just goes back to how the volume that we measure is tweaked by subtracting it by the volume of the particles in order to get the ideal volume. So it's essentially just correcting it in a way. Now, A is a coefficient, that means attractive forces, and B stands for a coefficient that measures the sizes of the molecules, which can be thought of as the bigness of the molecules, and that's why it's B. So this is called the real gas law, or the van der Waals equation, and it's right here. And we will use it in a future question that will be coming up very soon. So let's go on to our next topic. How does an ideal gas exactly deviate from the ideal gas and turn into a real gas? Well, gases deviate from the ideal gas when attractive forces and molecular size becomes prominent, as we saw in the previous slide where the attractive forces and molecular sizes affected our P and V. So this occurs when gases are closer to the liquid state, where the molecules are close enough to feel attractive forces, and where the volume of the container is so small that molecular size matters. So when does this happen? How can a gas be closer to the liquid state? Well, it can do that by decreasing in energy or becoming more dense. So gases that are closer to the liquid state and deviate from the ideal gas law happen at high pressures where there is tight packing and low volume. And remember, liquids have high density since they are tightly packed. And gases also deviate from the ideal gas law at low temperatures, since slow-moving gases are more likely to feel attractive forces from other gas particles. And in addition, at low temperatures, the volume is usually low, so they are more tightly packed in that regard. Now, aside from high pressures and low temperatures that can cause the gas to deviate from the ideal gas law, there are some other things that you could look at to see if a gas is likely to deviate. Gases are likely to deviate from the ideal gas law when the substance has a high boiling point, which means that the molecules have stronger attractive forces. And what I wrote in the note is that gases with high boiling points are closer to the liquid state since they can more easily condense. Now, how can you tell if something has a high boiling point? Well, there are a few things you could look at. If something is an ionic compound such as NaCl, then it automatically has high boiling point, and these things typically don't exist as gases, so we typically don't see those. But we typically see other things such as covalent molecules being studied as gases. So, looking at covalent molecules, high boiling point substances can be identified because some of them have high molar masses, and this usually applies to molecular compounds. So, for example, H2 has a low molar mass, so it won't deviate from the ideal gas law. Now, on the other hand, iodine gas, well, let me just write the states there just to be specific. Iodine gas has a very high molar mass, and things with high molar masses tend to have high attractive forces, since that's what it means to have a high boiling point. It means that you're hardest to boil off, which means that it's harder to break the bonds between the liquid molecules and send them flying off as gases. So things with high molar masses tend to deviate from the ideal gas law since they have stronger attractive forces. So now that we're done looking at this, let's look at a graph that shows the real measured volume divided by the ideal or predicted volume. So this graph will kind of give us proof for why at high pressures the gas tends to deviate from the ideal gas law. And this is what we pointed out before. At high pressures, gases deviate from the ideal gas law. So in this graph, it will most definitely prove that at high pressures, the volume will definitely deviate from the ideal volume. So at ideal conditions, even for real conditions, it's supposed to be a 1-to-1 ratio, which means that the real measured volume divided by the ideal or predicted volume should be 1. And that's under ideal conditions, assuming that there are no attractive forces or molecular sizes. But of course, in reality, these things exist. So that's why this graph will not be as ideal as we want. So in this graph, if Vm, which is the real measured volume, is greater than Vm with a degree symbol, which is, the ideal volume, then it will be greater than 1, because if this is greater than this, then, the fraction Vm over Vm naught will be greater than 1, and Vm over Vm naught will be less than 1 when the real volume is less than the ideal volume. And if you think of it as a fraction, if this is less than this, then the fraction will be less than 1. So that's how you read this graph. And let's now figure out why at this part, why the real volume is less than the ideal volume predicted by the ideal gas law. At low pressures, attractive forces between methane molecules pull methane molecules closer to decrease the ideal volume. What you are left with is a smaller volume when measured. So what this is saying is that, let's just say that our container can change volumes and is flexible, since that's an assumption that we're making. So let's just say that we have a container with some gas particles, and the ideal case is that, these particles don't have attractive forces, but in real life, there are attractive forces. So the actual volume, which is in green, is actually a little bit smaller because attractive forces pull the CH4 molecules closer to each other because they're attracted to each other, and this decreases the volume of the gas. So that's how that works. Now let's figure out why at this part the real volume is higher than the ideal volume, and watch how it just keeps on deviating further and further from the ideal gas law. Let's see why this happens. At high pressures, the volume of the molecules becomes significant, and this goes back to that picture that I drew here where the volume of the molecules became significant. Molecules cannot be compressed like empty space can. Okay? At high pressures, the volume of the container is supposed to be super small because at high pressures, the volume is small, assuming that your temperature and moles are constant. But since the volume of the molecules are significant and matter, let's just say that container, and let's just say that we have gases, and this is the ideal situation. But in the real situation, your gas molecules actually take up a lot of space, especially at high pressures where the volume is super small and the volume of the molecules begin to matter. So when they begin to matter, they actually take up space and make the actual measured volume greater than what is predicted by the ideal gas law. So this is greater than what is predicted by the ideal gas law. In other words, the actual volume includes both the ideal volume, or the volume that the molecules can move in, plus the volume of the particles themselves. So note how the real gas law has this idea embedded in it. So if we look back at the real gas law, we notice how if you combine these two terms, you get, I guess, the ideal volume that the gas always wanted but never could have because of the particle sizes, which kind of prevented that from happening. So if you notice, if this is the ideal volume and this is the measured volume, notice how the ideal volume is less than the measured volume because you're subtracting the measured volume by NB in order to get the ideal volume. So the ideal volume is less than the measured volume simply because the molecular sizes matter and they take up space. And we could rewrite this on the next slide. So we could say that the I don't know, the volume ideal is equal to the volume measured plus the sizes of the molecules, which we denoted as NB. Now, oh wait, is that a subtract sign? Oh yeah, it's a subtract sign, sorry. Alright, so if we manipulate this equation, we can see that the ideal volume plus the volume of the particles themselves is equal to the measured volume. And notice how that exactly matches with the explanation we gave over here. And that's how the real gas law relates to this graph over here. But, this part, I've been thinking about it, and I'm not really sure how the real gas law applies to that. I think for that part, you just have to draw some pictures and deduce some things. But in the end, both of these situations, both of these trends can be determined by drawing pictures and seeing what's going on and how the attractions and the volume of the molecules are affecting the ideal volume and making it, larger than usual, for example, on this side. So drawing pictures is very useful if you're trying to think about things. And this graph basically lets us conclude that at high pressures, the volume deviates extensively from the ideal gas. And that makes sense since we just talked about it. So now that the conceptual side of the real gas is covered, let's now cover the mathematical side to the real gas. So let's say we are given that the pressure of the carbon dioxide gas was 3.00 atms, 1.00 moles, and the temperature was 273 Kelvin. And remember how the real gas law had coefficients A and B? Well, these coefficients are unique to every gas, and for carbon dioxide, A is 3.610, and B is 0.0429, and these stay true as long as we use atms, moles, Kelvin, and liters. So if I use the ideal gas law to solve for the volume, then I get that the volume is equal to 7.47 liters. Now, what if I use the real gas law? So on the next slide, I used the real gas law by plugging in A over here, and this was n squared, and this was v squared. And over here, I plugged in, the n times the b, and I set it equal to nRT, because this looks just like the van der Waals equation we were talking about. So I just plugged it in, and I used an online algebra calculator because I honestly didn't really want to solve this on a whiteboard because it might have taken too long. And look how complicated it is. It has a v squared here and a v here, and I'm expected to solve for v. Well, you could graph this, and I don't know how exactly you would find it, but if you know your math, there are ways to do this question, but I just decided to plug it into an online calculator. I got that the real volume is actually 7.35 liters. So the volume measured is supposed to be 7.35 liters. And notice how the real volume is less than the ideal volume measured by the ideal gas law. And doesn't this look like this over here where the real volume was less than the ideal volume? Well, yeah, at low pressures, the real volume is less than the ideal volume for many gases, including carbon dioxide gas. And I just kind of proved it here that the real gas volume was lower than the ideal gas volume, and that reflects in the graph. So that's all I wanted to do in this video. Feel free to pause and look at the work and plug it in on your own if you're curious. And one last thing I forgot to mention, this graph is a graph for methane gas, so that's why I put methane there. So this graph is graphing the relationship between the real volume and the ideal volume for methane gas. So I forgot to mention that. But after mentioning that, that's all I wanted to talk about, and thanks for watching. Have a nice day.